Okay, we're beginning our discussion and we focus on a wide range of things, but most importantly, we're going to look at um, arrangements of objects. In this case, we're looking at the arrangement of 6 zeros, 4 ones, 3 twos are there. Or how many arrangements of the 6 zeros, 4 ones, and 3 twos are there in which the first zero precedes the first one? Okay. Now we need to obviously just count quickly and realize what's happening here. So first things first, we have how many positions? So we have 6 positions here. Right, in which case you have 4 positions. And here we have 3 positions. These are positions. Okay. Or if we have 4 plus 3 plus that, so we have a total of 6 plus 4 plus 3, which gives us 13 positions. 13 positions. Okay. And hence we start the solution as follows. Excuse. Right, we start the solution as follows and say, what did I do? Right, I just tempered into that. Okay, it's fine. Right, so once again, the number of positions. Right. Equals 6 plus 4 plus 3. 6 plus 4 plus 3, which equals 13 positions. They are 13 positions. 13 positions available. There are 13 positions available. Right. Okay. 13 positions available. Right. Altogether for the arrangement. There are 13 positions available for the arrangement. Right. So we are looking at the arrangement such that in which the first 0 precedes the first 1. So the first 0 precedes the first 1. Okay, as said. Right. So we decide to choose or place the 3 twos. In how many ways would you place the 3 twos? So you will place them in out of 13 positions. You will choose 3 positions to place the objects. What is happening here? Right. Out of the 13 positions altogether, let's just say that to simplify matters, it's the same thing. You can draw diagrams and things, but right. Out of the 13 positions, you choose 3 positions in which you place the 3 twos. The reason it's easy to place the twos because there are further conditions on the 0 and the 1. So we do not have restrictions quite on the twos. So we have much freedom So we can easily place the 2's. Okay. Because it's easy to place the 2's, what do you do? So you're going to choose 3 positions and place the 2's amongst the 13 positions. So we shall therefore say 13 positions, choose 3 ways. Okay, you can simplify that, but yeah, normally simplify the end. Just use the same approach as recommended. So we shall do that. We shall place the 2's in 13, choose 3 ways. Okay. Now we come to the condition where now they are suggesting how we need to place the 0 and the first one. Right. So with those conditions, we then put those into focus. Right. So we shall then say now, right, put the 0 because the first 0 precedes the first one. So now put 0 in the first of the remaining positions. Of the remaining positions. Right, now put 0 in the first because 0, which the first 0 precedes the first one. So we'll have, after having placed the remaining positions, but now you must put 0 first in the remaining positions because it must come first before the first one. So because you put 0 in the first of the remaining positions, there's one way. One way for this. Okay. How many positions are left? Because we have chosen 3 positions, and now you have a position to put the 0. So you continue. Now, then pick 5 other positions. 5 other positions for the remaining zeros. Because there are 6 zeros. You have just placed 1 0, and then we have 5 zeros left. So then pick 5 other positions for the remaining zeros. For the remaining zeros. Which can be done in how many ways? In how many ways can this be done? So obviously, out of the 13, you subtract 4 positions that have been filled. So we're left with 9 positions. And these can be done in 9 choose 5 ways. 9 choose 5 ways. What is then the total number of ways? Because now we have so what is then the total number of ways to do this? What is then the total number of ways to do this? So the total number of ways so you have a sequence of processes to perform. So first we placed the three twos because they were easy to place without any restrictions or conditions on the twos. So we chose three positions out of the 13 positions. Then the next positions were putting the zero first, because now we must say we're told that meter zero precedes the first one. Right, so, but if we decide to put the zero first, we did that in one way. And then now we can put the other zeros in the remaining positions in 9 to 5 ways. After having put the zero first, then would have satisfied the condition required. Okay, 13 choose 3 would be 13 factorial. 13 minus 3, yeah. 13 minus 3. Okay, just remember the combinatorial symbol. N choose R is N factorial. N minus R factorial, R factorial. 13 minus 3, 3 factorial. And then 9 factorial. 9 minus 5 factorial. 5 factorial. Okay. So we have satisfied the main conditions of putting the zero first. And that was done in one way, and we were able to arrange the rest of the zeros amongst the remaining positions. And therefore, the remaining calculations can easily be done in this manner. All right, obviously one can use a calculator to do this one, but one can also just simplify these. Normally, because the numbers are very large, students are not encouraged to simplify these. So that is going to be 10 factorial, 3 factorial. That's going to be 9 factorial, 4 factorial. That's going to be 5 factorial. And that's going to be 13. So 13 factorial. You can reduce 13 factorial to 10 and cancel that. 9 factorial, you can reduce it to 5 factorial and then cancel out. And then obviously use a calculator to simplify the rest of this. Or you can use a calculator to just do it from the multiplication at the beginning. So, right, so another student can come and say 13 factorial is 13, 13 minus 1 is 12, minus 1 is 11, and then you have 10 factorial. You divide by 10 factorial, 3 factorial. So the 10 factorial is going to cancel. 9 factorial can be reduced to 9 minus 1 is 8, minus 1, 7, minus 1, 6, and then 5 factorial. And then you have 4 factorial, 5 factorial. So you cancel these here. The 3 factorial is 6. So 6 cosine times 6 divides the 12, giving us 11. Okay, 5 factorial cancels out. And then 4 factorial is the same as 24. Can you put 24 there? 9 by... Hey, can you look at how 24 further divides the whole thing? Yeah, okay. Because 8 by 6 is 48. You divide 48 by 24, is only 2 by 7, and then you just do your calculator work, and then the answer will have to be this one here. So we have managed to organize these. So we have arranged this, or the number of ways is these ways. Okay, so to arrange this is just a question of the positions. It's a question of positions. There are 13 positions, etc. So it's a question of positions than anything else. Right, so next question. Right, fulfilled. Right, so obviously the repetitions here. How many arrangements of the letters in fulfilled have all the following properties simultaneously? Okay, so we are looking at the properties. Okay, this is very popular in this module. Now, no consecutive Fs. The vowels E, R, and U are in alphabetical order. The three letters, the three L's are next to each other. That is, they can be grouped like this. Okay. Let's look at these. So we're asking how many arrangements of the letters in fulfilled have all the following properties. Right, so the easiest way is to always say those letters that are grouped together. Grouped uh, grouped together. So those ones become the easiest. So now you deal with them as one object. Like in this case, the three L's, they're actually put together. So now, right, so the first thing is that treat L as a single letter. Okay, it's easier. So how many letters are you left with? Right, so if you treat those ones as one letter, so you have F, U, so I'm going to look at the list, and then L. Okay, there's another F. You have I here. You have E and D. Okay, you have just that list. You can put and D there, but yeah, you have that. Okay, what is the next thing we need to do here? Right, right. But now we have no consecutive Fs. So how many Fs are there altogether? There are two of them. So no consecutive Fs, this one. So we consider that. No consecutive Fs. Right, no consecutive Fs would mean we have some letters and then F, and then here you put non-F. And then because there are only two, and then you can put other letters there. But they can't be consecutive. So you have this arrangement. Okay. It's just a rough idea. Okay. Right. There is a property of distributions. Right. So we learned the distributions when it comes to this concept here. Right. So we shall speak about distributions now. Right, how do we perform these distributions? Right, let's discuss the property of performing a series of distributions. Right, a series of the distributions. Right, so these distributions can be done in a couple of ways. We have learned yesterday a property that allows us to perform distributions, but there are more formulas that we need to understand for us to be in a position to perform a series of distributions. Right. Okay, so we're going to discuss that in a minute. I want to give one formula that we use to understand distributions very well. Right. There's a formula I want to give that is going to help us to understand distributions very well. Right, so we learned the formula of the combinations yesterday, so I'm just going to repeat that one. Right, so we learned the formula, this one here, for distributions. Right, there's a small variation. I'm just going to give you one formula of the distributions. One formula of the distributions in a second. Right, so we need to know that to perform a series of the distributions, we learn the following formula. We learn the following formula. Just 1 second, I'm going to actually write it down. Okay, because there are variations. Okay, so the distributions, either you're distributing R, so if you distribute R identical objects, okay, because there are a couple of formulas to learn. Into, you distribute R identical objects into N different boxes. Okay, what is the formula? Okay, that's the statement. So you distribute R identical objects into N different boxes. So it is N choose R plus N minus 1 R. Yeah, and so these can be written like, okay, can be written as R plus N minus 1 factorial, R factorial, and then N minus 1 factorial. Okay, so you can write it like that. You can leave it like the other one. Okay. So these have to do with identical objects. And then I'm going to look at distinct objects. Okay, if you distribute distinct objects, what is the formula? Okay, now this is the case, we get so we have R, R1, R2, Rn distributions. Okay, we shall speak about the if you distribute distinct or different objects, but now we are looking at the distribution of objects that become more identical. So um, right, so then you distribute the, how many objects are there altogether? Okay, so if you take the F's and you fix them, so you're left with how many objects? Okay, this one is like one, so it's 1, 2, 3, 4. Right. How many objects are not F? So you'd have 1, 2, 3, 4, 5. Okay, this is what we do. Okay, then distribute um the remaining. Okay, there will be 4 non-Fs in the 3 boxes. Okay, if you are to look at the 3 boxes, in how many ways? Right, so because now you are dealing with the 3 boxes, okay, we are looking at the 3 boxes. Okay, you pause to think about actually what is being said here. Okay, we have made available 3 boxes because of the restrictions. So this is a box and a box and another box. Okay, so into n different boxes, this is can be written as, you can write it as 3 plus 4 minus 1, 4 here. Okay. So obviously we're dealing with R identical objects. If we have look at how many identical objects are there in the 3 boxes. And so we realize therefore that we shall be dealing with um 3 boxes. And we can always look at these as involving, as we said, we actually distribute the remaining 4 non-Fs. 4 non-Fs. In the 3 boxes. Okay, because obviously we said the 3 L's are next to each other. The vowels E, I, and U are actually in alphabetical order. So if you have the vowels E, I, and U are actually in alphabetical order, so we have 1, 2, 3, 4 positions. So the 4 non-Fs in the 3 boxes are put that way. We've counted a total of 5, but you can see that these ones here are in alphabetical order, and therefore it suggests that they are already organized, giving us 4 non-Fs, meaning that we shall be dealing with F. Right, so normally these are in alphabetical order. Right. we can organize them in, they form a string. Okay, that is clear. Okay, I want to say something else. So these should organize like this, and therefore it's going to become 6, 4. 6 choose 4. 6 factorial, 6 minus 4 factorial, 4 factorial. And the result is only 15. Okay, can use a calculator to do that. It's not a problem. And even if your answer is 6, choose 4. Or 6 combination 4. So now this is actually, this is going to give us exactly 15 patterns. Right, next we calculate the number of the ordering of the non-Fs in their 5 positions. Okay. Determining the ordering of the non-Fs in the 5 positions. In the 5 positions. Okay. Okay, the positions obviously would be 1, 2. The objects are themselves 1, 2, 3, 4, 5. Non-Fs in the 5 positions. Obviously, the arrows is just one symbol. You can look at it as one symbol. We note therefore that this one, this triple L is just like what? Like one symbol, so L can sit in any of the positions, in any of the 5 positions. So this one can be placed.
Hello.
Yes, please.
Can you explain where you got this from?
Oh, this one. Okay. So obviously in this case, we are speaking of distributions, and now it's exactly coming from this formula where we say distribute R identical objects into n different boxes. So here we actually, because the condition is that we have no consecutive Fs. So if the Fs are not to be consecutive, there are only 2 Fs in the weight field. And therefore, but we need to make sure we separate them and put symbols in between before and after so that they are non-consecutive. So that gives us 3 boxes. Okay, so obviously in this formula here, you actually will therefore be dealing with n, the n stands for the number of the boxes. Right, and there are 3 of them. So we'll just put the n here for 3. And then now, how many are the identical objects, or are the objects we actually are putting into the boxes? Right, we've already said that the objects that will be put there would be 4 objects. All right, we agree that we're counting 1, 2, 3, 4, 5 non-Fs, but this is the triple L is 1, but now we then have what? We then have that the vowels, just, we can regard them as one symbol. So the U, the E and the I are 1. So it's 1, 2, these are vowels, right? So it's 1, 2. So obviously if you count 1, you count 1 for the vowels, right? So, and now if the vowels are there, and this one therefore is 2, right, so you have 3, and therefore ultimately you have 4 non-Fs in the 3 boxes. How many non-Fs will therefore be there? There will be actually a total of 4 non-Fs. Okay, let's look at that carefully. Let's set ready, you look at the non-Fs. What are non-Fs? Are the vowels, the L's, the R, the E, and the D. Because these vowels are in alphabetical order once again, so E, I, and U will be organized in alphabetical order, giving a pattern and a string. So those ones you can regard them as a symbol, right? So if you do, that gives us the distribution. Then we distribute the remaining 4 non-Fs in the 3 boxes. Right, in the 3 boxes. Okay, obviously, we're looking at the entire word fulfilled here. And the Fs would be separated and giving us a total of 3 boxes. And with the grouping of the 3 Ls, the vowels, etc., we have a total of 4 non-Fs in the word fulfilled. Okay, you can always look at how that you can organize that and think of that very clearly and make sure that these are, so you have the Fs are out. You want to arrange them so that the Fs are non-consecutive. So how many non-Fs are there? You'd have the U, the vowel, the I is a vowel, and also the E is a vowel. Cross, cross, cross. So crossing them meaning they're just one thing. Right, so now you then have the Ls. Right, so the Ls are also one symbol. Right, so you think of that very carefully. Right, so try to think of that. Try to think of that. Okay, we'll look at that carefully, but I want to mention a couple of things. I was then saying the non-Fs in the 5 positions, if you count 1, 2, 3, 4, 5. So the non-Fs can be placed in the 5 positions. So if there are 5 positions for the non-Fs in the
Hello.
yes, please.
I'm confused about how you got 4 non-Fs.
Okay, because you think it must be 3.
Yes, shouldn't it be?
Right. Okay, I'll get back to that in a minute. That's fine. I'll get back to that in a minute. Okay, I'll get back to that in a minute. Right, but now let me first say determining the ordering of the non-Fs in the 5 positions. So obviously you'll have 5 positions, 1, 2, 3, 4, 5. Okay, I'll get back to that. Then we have the LLL can therefore be actually placed in 5 ways. In 5 ways. Why 5 ways? Because 5 positions of the non-Fs. 5 ways. I'll get back to that observation. 5 ways. Okay, just one sec. Right. Um, After that, you'd have placed the triple L in 5 ways. Then we have the letter D. Then the letter D can be placed in how many ways? Okay, obviously now we have placed the L's, and therefore we have 4 positions left. So the D can be placed in 4 ways because we have 4 positions left. Out of the 5, the triple L have taken 1 position, and therefore you have the D can be placed in 4 ways. Moreover, the vowels. Over the vowels, okay, the vowels are A, E, O, U. Right, so in particular, the vowels E, I, U. Obviously, they're to be placed in alphabetical order. So they must be placed in alphabetical order. Okay, I'll get back to your observation, please. Right, alphabetical order. Right. Right, so obviously they must be placed in alphabetical order in the remaining three places. Okay, because you had four places, now we have remaining three places, you have placed the D, so you have the remaining, in the remaining three places. In the remaining three places. In how many ways? Right, so they can be placed in the remaining three places in one way. Okay, think about that. In one way. Because they must be in alphabetical order. Right, so hence, I'll go back and read check, right. Hence the total number of arrangements right, the total number of arrangements is equal to, right, we got 15 ways here. Okay, I'm gonna cross check and see if there's something to rectify. And then for the non-Fs, we had 5 positions and 5 ways. And then we had the 4 ways. And that would give us 300 ways for all the arrangements. Okay. Okay, I want to come back to this. I want to state a condition before we relook at at the observation you made. It's a brilliant observation. But I want to first speak about identical objects and the properties that encompass this. Right, there's a statement we learn, and the statement says the process of distributing. Okay, there's some detail here, and I want us to look at this statement carefully. The process of distributing are identical objects into n different boxes. Is equivalent to choosing in ordered to choosing an unordered subset of R box names. Like I'm just giving the rule we use for these quite in some about 3 to 4 lines. Okay, right. The process of distributing R identical objects into n different boxes. It's equivalent to choosing an unordered subset of R box names, right, with repetition. With the repetition from among the n choices. Of boxes. Okay, we say thus they are R plus n minus 1 R, which we can write like that. No worries about that. Choose the formula. R factorial n minus 1 factorial. Distributions. I want us to analyze this statement carefully. Distributions of the R identical objects. Okay. So we're saying the process of actually distributing R identical objects into n different boxes is equivalent to choosing an unordered subset of R box names with repetition from among the n choices of boxes. Thus, there are R plus n minus 1 choose R, which are in the factorial quotient as given. Okay. I want to give a description before we move on. I want to give a description before we certainly move on. Okay. I want to give a description before we certainly move on. Okay. Right. So what is the meaning of this statement here before I go back and then move forward? I want us to pause and reason how this formula works and how this formula can be used. But also, I want us to analyze the process of distributing R identical objects into n different boxes. Right, so, but I want to look at a typical example that is going to highlight the case that's very important. Did I leave space here? Okay. Let me look at the green example very shortly, and then we shall go back and conclude our previous discussion. So I want to look at a brief example. That's a little bit different from what you look at. It says how many ways are there to distribute 20 identical sticks of red licorice, right, licorice, and 15 identical, 15 identical, 6. Okay, this is quite an interesting example, but quite short and nice, of black licorice among 5 children. 5. Okay, how many ways um are there to distribute 20 identical sticks of red licorice and 15 identical sticks of black licorice among 5 children? What is the answer to this in view of that formula? Right, so I want us to look at the answer together. What is the answer to this? Let's look at the solution to this. And then we shall go back and then move forward to a different question. Right, I want us to say, we're using a model here. So using the identical objects model. It's just a model we are using here. Objects model of distributions. So for distributions, what do we do? We see that the ways to distribute 20 identical sticks of red licorice among the 5 children can be seen as equal to the ways to select a collection of 20 names. So the 20 identical sticks can be seen as equivalent to 20 names. These names can be seen as sort of destinations. From a set of 5, different names. Different names with repetition. Okay, just it's like we're analyzing the green case here. Thus, how many ways can this be done? So if you use this formula R plus N minus 1R, what is R, what is N becomes the next question. Right, so we can see that obviously we're actually looking at the identical objects. So if we're looking at R, identical objects, so we have 20 identical sticks, and therefore this will be 20. Right, you can write it as 20 plus 5 minus 1. And this is okay. We shall simplify these. We can use a calculator to simplify these. But we are really saying we want to distribute this 20 red 15 black liquorize among the 5 children. So we actually are therefore seeing that the identical objects are 20, and then the children themselves are 5 because we have 5 different names. So we have this. Okay, using calculator, this is 10, 10,626 ways. Okay, okay, you just think of that, but I want to mention this. Right, using the same reasoning, now we dealt with the 20. What about the 15? Now we deal with the 15 identical sticks of the black rigorize. So moreover, so you have 15 plus 5 minus 115 for the other color. Because the 20 are red and then the black. Okay, so the 15 are black. And if you use a calculator here, you get 3876. Okay, we're looking at logical reasoning here, and that's the point of doing these examples. We're trying to make sense of the principles in a way that applies to all the problems uniformly. Right, so we are then saying the distributions of the red and black rigorize are become disjoint. The multiplication principle applies, and so because that is joint, we use the multiplication principle. And so number of ways to distribute the red and black, total number of ways equals 10, 6 to 6 by 3876. And the answer is what? 1,186,376 ways. Okay, so you pause to think about this. You pause to think about this. Okay, but this will be how we can look at the licorice example, and the 5 children, the 20 sticks and the 15 sticks, 20 red and the 15 sticks of a different color. Perhaps this is a much more very direct and very simple example, because we are effectively saying here you are dealing with R identical objects and you are doing it in different boxes. So here you dealt with the 20 black or red, 20 red licorice, and now the boxes can be perceived as the children. And now the recipients are children. So you are like putting these licorice into boxes, and these boxes are names of the children or are the children themselves. Right. Okay, we're going back to the example. Right. Obviously, we have discussed the solution, but I want to look if there's anything we need to analyze and modify as you suggested. So we're going to actually quickly just go through that. Right, we're looking at the arrangements of, I want to just press through and make sure that the reasoning is correct here. Right, we're looking at the arrangements of the letters in the word fulfilled. Right, so we said how many arrangements of the letters in fulfilled have all the following properties simultaneously, no consecutive Fs. And that meant no consecutive Fs. The two letters F. So we decided to separate them and put boxes on either side. So we put like 3 boxes in which you can like slot in things. All right. So the question then is, how many objects would therefore be the identical objects here? That we need to now, because now we're looking at we're using these model on the other side. But how many objects would therefore perceived as identical? Okay, right. So we are removing the F's out of the picture. And we are dealing with the remaining objects. Right. And you are saying obviously the vowels E, I, and U are in alphabetical order. Right. So if they're in alphabetical order, they can be obviously ordered alphabetically. And we have analyzed that, and we shall go back, we shall proceed to analyze in wherever we wrote it in the story, in the solution. Right, the 3 L's are next to each other, so they form one symbol. So if they form one symbol, I looked at this word and I put the first F, and then I actually put U, and then I grouped all the 3 L's, and then there is another F, and there is I, there is E, and there is the letter D. All right. Now I want us to look at which objects are identical and which objects are must be put into the boxes, because now in the boxes we put, using that model, we put identical objects. So what are those objects that are identical? Right, so obviously at this point we have separated, we went on to say then distribute the remaining 4 non-Fs in the 3 boxes. So the question is, how many non-Fs are there? Right, we counted the U, the I, and the E as one symbol. Right, and then now we looked at the L's as another symbol. And then we looked at the D as one more symbol. Right, so the question therefore is, how many non-Fs are there altogether? How many non-Fs are there altogether? Okay, so somebody counts U, I, and E as one thing, because they must be together. They must be in alphabetical order. And obviously you have the L too, and you have the D3. And now they must be put in the 3 boxes. So that's fine. And then now we proceed to say, obviously, determining the ordering of the non-Fs in the 5 positions. We counted a total of 5 positions: 1, 2, 3, 4, 5 positions. Okay, we'll continue. I'm just analyzing this with you now so that um, um, we continue. Okay, we continue. Okay, I'm just looking at this carefully to make sure that everything is okay. So obviously we dealt with the 5 positions: 1, 2, 3, 4, 5 of the non-Fs. Right. So the L's are placed in in 5 ways. Then the letter D can be placed in 4 ways, because after you have placed the L's in the 5 positions, then you'd have 4 positions left, and then in the 4 positions left, you can place the D. Right. Moreover, the vowels E, R, and that must be placed in alphabetical order in the remaining 3 places. Okay. Okay, continue. All right, in the remaining three places. Okay, I'm with you now. Just need to make sure that everything is okay. In one way, that's fine. And hence now the total number of arrangements is that. Mhm. Okay. And now we're just discussing the idea, this one, the statement. Then distribute the remaining four non-Fs in the three boxes. And we realize that it would be a U. Okay, I'm trying to look at that carefully. It will be a U, it will be LLL, and it would be the UIE in order. But yeah, this must be placed in order. I'm not saying they're in order. You can just place them in order. And then we have the D. And then we're counting three non-Fs. Right. And that means that we need to change here. And so now we are dealing with a total of the, so now this is going to be three. Okay, need to obviously check these things like this. Because now we're dealing with how many different boxes? We're dealing with n equals three boxes, but now we counted three objects to regard as identical. Okay. Right, so you need to always be extra careful. Need to be always be extra careful. Right. So this one is going to become 5, 3, 5. And then this one is going to become what? 5 minus 3. And this one is going to become 3. And this one is going to become 5 by that. So this is 5 factorial, then you can simplify this. This is 2 divided by 2 factorial, 3 factorial. Right, so what is this? This is 5 by 4, 3 factorial cancels, leaving us with 2 factorial, and therefore this is 10. So you come here and put 10. Okay, it's an interesting observation you made. I mean, that's very logically acceptable. The rest is fine. So you'd have that. And this would be 10 by 5, which is 50 by 4, 200. 200. Okay, yeah, that's correct. Okay, we'll continue. Right, so we look at question 9. Right, question 9 is a very interesting one. So it comes all the time in the exam, but like all the time. Right, find a recurrence relation with initial conditions for the, right, so we're dealing with recurrence relations and now they're part of the exam. So, but this section is quite straightforward, so it's not a very difficult one. But you just need to know the methods of how to deal with recurrence relations. We'll spend some time on the recurrence relations that are examinable. write their word story sums, word problems that really emerge from this. But let's just look at the kinds of methods we can use, like this problem. Okay, we continue. So now find a recurrence relation with initial conditions for the number of n-digit ternary strings. Ternary strings are those strings with 0, 1, and 2 without any occurrence of the substring 0, 1. Right, and the marks are 7. So you need to just get your reasoning in order here. You need to get your reasoning in order here. Okay, let's just do this one together right now. Right, how do we find the recurrence relation its initial conditions for the number of n digits when n is bigger or equal to 1, okay, of those ternary strings. Ternary strings have those 3 digits, 0, 1, and 2. Right, first things first, we start like we do word problems if in matric at school. We let an be the number, of such n digit ternary strings. Okay, we continue. So this an is the number of such n-digit ternary strings is the unknown, because we need to find the recurrence relation for the number of those n-digit ternary strings. So the unknown is the an, a sub n. Right, so then, okay, let's look at this. If you were to say, then the number of n digit, right, the number of n digits, okay, you continue. Right, so then the number of n digits, ternary strings, ternary strings, okay, we continue. Ternary strings with 1. Okay, let's look at this. Right, so obviously in this case, you are interested in finding the known an, the recurrence relation. Right, the number of the n-digit ternary strings with 1. Okay, is what? Right, so it is actually an minus 1, because we're looking at the n-digit ternary strings. But in the n-digit ternary strings, we're removing 0, 1. So it's minus 1. Right. Okay, I need to write that one carefully. Can I write that one? Because it's important. Um, okay, continue. Okay, let me write that one a bit in detail because I want this to be very clear. It's a concept that can be very potentially confusing. With 1 is an minus 1. Okay, so why this an minus 1? It is to, let me just describe so that this is there. Since such a string can be completed can be completed with any n minus 1 digit ternary string not containing the substring substring um, not containing the substring 01. Okay, so we are looking at the n digit ternary strings, and we are removing the substring 01. If we are removing the substring 01, then we shall say then the number of the n-digit ternary strings with 1 is an minus 1. We're removing a string. Okay. Moreover, we say this. Okay. Because this is exactly the method of reasoning. Moreover, the number of such n-digit ternary strings starting with 2. Right, so is also. Okay, the number of the ternary string starting with 2 is also what? So we remove 1, the number 1. So is also an minus 1. Okay, so we actually are looking at the n-digit ternary strings starting with 2 is also an minus 1. Okay, there's also a statement here because we have those Those strings that begin with 0, how do we deal with strings that begin with 0? Because the ternary strings contain zeros, ones, and twos. Right, so those that begin with 0, let's give a statement that's a bit more clearer here. Right, but if the n digit string starts with 0, it can only be completed with an n minus 1 digit string. Okay, let's look at this. Right, but if the n digit string starts with 0, yeah, I'm saying we're looking at those that start with 0 and the significance of those. It can actually be completed with n minus 1 digit string. So if you have a string that starts with a 0, you can complete that one with the n minus 1 digit string, because you can put associate with it an n minus 1 digit string, and then it's going to become n minus 1 with the 0. So you'll get an n digit string, because you have n digits, and then you have 0. You have n minus 1 digits and 0. So n minus 1 digits and 0 will give you an n digit string. Okay, nothing strange there. Okay, but we state therefore that which does not. Normally there's a question like this that come in this exam. Which does not begin with 1. Which does not begin with 1. Obviously, we are looking at a string that starts with 0. So surely it can be completed with, so you can put an n minus 1 digit string which does not begin with 1. Why must the string not begin with 1? Because if then you're going to have the 0, 1, but you don't want the 0, 1. So if you start with 0, then the n minus 1 digit string cannot begin with 1, because you're going to have 0, 1. So we avoid that. What is the number of such strings? The number of such strings. The number of such. Right, of such things is. Right, so the number of such strings is an minus 1 minus an minus 2. Okay, we're going to analyze all these to make you understand the sentences here and the claims that are made in this. But hence, what is then an? Where an is the number of such n-digit ternary strings. For an can therefore be seen as follows. It can be seen as twice an minus 1 plus an minus 1 minus an minus 2. An 3an minus 1 minus an minus 2. N greater equal to 3. Okay, I want us to analyze these together and make sure that every statement, every sentence is clear with A1 equals 3 and A2, if this one is the number of such n-digit strings, right, so A1 is 3, and what is A2? What is A2? Okay, we analyze this together, but we argue that A2 is going to be 3 by 3, 3 by 3 minus 1. But 3 by 3 is 3 squared, so that you get 8. And this gives, these two give the initial conditions. But let's analyze these together and make sure this is very clear. Right, we recap on the claim, but first the question. Right, remember that we had to find a recurrence relation with initial conditions. So these are the initial conditions, A1 and A2. For the n digit where n is greater or equal to 1, ternary strings, once again, that contains 0, 1, and 2. Those are ternary without any occurrence of, we just remove the string 0, 1. This question is there most of the times, and I have a strong feeling it is there even this time around. It can be exactly like this, or there can just be a modification of the string that is being removed, but very likely it's going to be exactly like this. They can remove 1, 2 string. So how do you analyze this question? So to analyze this, we say we let an to be the number of such n-digit ternary strings. So it's the number of the strings, n-digit. Right, then we proceed to say then the number of the n-digit ternary strings with 1. Right, because we are looking at the 0, 1 condition. So now we're looking at the number of the n-digit ternary strings with 1 is actually an minus 1. Why is it an minus 1? Since such a string cannot or can be completed with any n minus 1 digit ternary string not containing the substring 0, 1. Yes, because we're not supposed to have the 0, 1. Right, next. Moreover, we note that the number of such n-digit ternary strings that start with 2 is also an minus 1. Okay, so we proceed from that. But if the n-digit ternary string starts with 0, it can only be completed with the n minus 1 digit string, which does not begin with 1. The number of such strings is an minus 1. Okay, so obviously you can see that we have an minus 1 for the number of the n-digit ternary strings with 1. So there's an a sub n minus 1. And also the n-digit ternary strings with 2, right, are also an minus 1. . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . right? And moreover, so we have an minus 1 and n minus 1 for the 1 and the 2. And then now we look at those that starts with 0. They can be completed like that. Okay, so you have an for the 0, the strings for those strings that begin with 0. So you'll have the an minus 1, right? Because you said that, but if the n-digit string start with 0, it can be completed with n minus 1 digit, with an n minus 1 digit string which does not begin with 1. So because you start with 0, then you can't start the other string with 1. So you can complete it with an n minus 1 digit string, and hence the n minus 1. Right, the number of such strings is then what? Right, so the number of such strings, therefore, is an minus 1 minus an minus 2. Right, so you actually, therefore, are looking at those that begin with 0, and you subtract the n minus 2. You subtract the n minus 2. So the understanding is that in those strings that begin with 0, you remove this substring. In those that begin with 0, you remove this substring. And this substring obviously is a 2-digit string. It's a 2-digit string, so you subtract that, the n minus 2. And therefore, this is what you get. So this is 2. Why is this 2? It is 2 because of the n.
Hello.
Yes, please.
Can you explain this part?
Yes. Okay. Yeah. I'm trying to explain that part. So obviously, we understand therefore that if you let n be the number of such n-digit ternary strings, so it's the number of all the strings, the n. So the number of all the strings is formed by the possible combinations of the strings. But the first string we looked at is the n minus 1 string. N minus 1 is the number of the n-digit ternary strings with 1. Right? So the number of the ternary strings with 1 is an minus 1. Right. And then now we have the number 2, the number of ternary strings with 2 is n minus 1. So there's n minus 1 for the strings that have 1, and there are those strings that have 2. Um, by 1, we mean the strings that start with 2 and the strings that start with 1. So there's going to be an minus 1 for the strings that start with 1. Some strings will start with 2. So there's an minus 1 for those. So there's n minus 1 plus n minus 1. Now we are dealing, this case here is for the case of those strings that start with 0. Right, so the strings that start with 0, we note that they can be completed with n minus 1 digit strings which do not begin with 1. Okay, but now we must remove, in the strings that start with 0, you must remove the 2-digit strings, this substring. So you subtract an minus 2. Why is this 2 here? Because it's 2 for those strings that start with 1, the strings that start with 2. And then this case here is for the string that start with 0. But you just remove from the string that start with 0, you remove the 0, 1 string. Okay. I want to add this one here. So we're saying, therefore, the number of n-digit strings which start with 1. Okay, if it starts with 1, we can complete it with an n minus 1 digit string. Okay. But now there are those strings that start with 1, those that start with 2, because either the string starts with 1 or 2 or 0, because we're dealing with ternary. So yeah. So um okay, continue. Okay, continue. Um okay, either a string starts with 0 or 1 or 2. So we started with if they start with 1, they can be completed with an n minus 1 digit ternary string. All right, so if that is the case, so you would have, therefore, because the an is the number of such n-digit ternary strings, so you therefore have, because if it starts with 1, then the string you'd have an minus 1 be the number of the n minus 1 digit ternary string. So you start with 1. So in other words, this is a counting principle. So if you start with 1, then you are dealing with n minus 1 simples. And then here the next one start with 2. You start with 2, so for it to be an n-digit string, you could complete it with n minus 1 digits. Or an n minus 1 digit string. Okay. Now, so this an minus 1, there are two of them. So the string start with 1 and the string start with 2. You'd have to just extend, because why do you extend? You put the rest of the digits so that you have an n-digit string. This one is the number of the such n-digit ternary. We are dealing with n-digit ternary strings. Sorry, having 1, how many digits do you add to make sure you have n digits? You must add n minus 1, n minus 1. So this one is for those strings that start with 1, those that start with 2, and this one is for those that start with 0. So there are two cases for those that start with 0, like we've said here. Right, but if an n-digit string starts with 0, it can be completed with an n minus 1 digit. If it starts with 0, how many? Because it must have n digits. So how many digits then do you add? You add an minus 1, which should not begin with 1. Right, after since they do not begin with 1, but also you subtract from this the number of such n-digit ternary strings. You subtract those strings that have 0, 1 substring, and you get that. So the 0 case brings about this difference. Those strings that start with 0. And yeah, this is those that start with 1, 2. And then you add this up. But obviously adding this up now, then the n can only begin from 3 upwards. Why? Right, because then you're going to have, because you have n minus 2. And then you can start from a1. Right, a1 obviously would be, because if an is the number of such n-digit ternary strings, so a1 would be the number of such 1-digit ternary strings. How many 1-digit ternary strings? Because an is the number of such n-digit ternary strings. How many 1-digit ternary strings? One digit can either be, so this one, or that one. So there are three of them, 0, 1, and 2. So they are one-digit strings. So there are three of them. What about A2? Two-digit strings, right? Or the number of such two-digit ternary strings. The two-digit ternary strings, so you can count those. So you pair this up. But now you must just subtract the 0, 1. If you pair this up, there are 1, 2, 3. There are two digits. So the two digits, there are a couple of ways to do that. So you can look at the two digits for this. So you have three choices for the first one. After you have, in how many ways can this be ordered? Three choices for the first one, for the first digit, because you are dealing with two digits. So you are dealing with two digits. Three choices for the first digit, because you're dealing with two-digit numbers like 1, 2, two-digit sequences. And then here, now after you have these three choices for the first digit, and then after that you have three choices for the second digit, but obviously you can do repetitions here. Okay, you can do, because you can have this, the string 2, 2 is allowed, because it's only a string 0, 1, so you must subtract 1. And this therefore becomes 8, 3 squared, which is 8. So yeah, so this is the answer to the question. Okay, try to understand this. Okay, next question. Okay, let's solve some recurrence relations like this one. Okay, normally you must be able to solve some of them like these. Let's solve this one for 5 marks. Normally solving this is not difficult. It's pretty easy, but there's just a couple of rules that you need to use. We use the alpha method. Right, using the alpha method, I've made space available. Yeah, it's not difficult, this one. So what you do is you use the alpha method. What is the alpha method? You let an be equal to alpha n. That's the method you use. Alpha superscript n. Then the characteristic equation is, then the characteristic equation is, okay, we come to the recurrence. So if we have an equals 7, an minus 1 minus 6, an minus 2. So we will have alpha to the n equals 7, alpha to the n minus 1, because if an is this, then an minus 1 is just alpha to the n minus 1. And then this one is 6, an minus 2 is going to be alpha to the n minus 2. Okay, now this one, you multiply by alpha squared, both sides, because you have alpha to the negative 2. So if you multiply the left by alpha squared, and multiply the right by alpha squared. So alpha to the n plus 2, alpha to the n plus 1, minus 6 alpha to the power n. Okay, do it like this. Okay, after this, remember this alpha, we just assume that this alpha is not 0, because even a0, it's the a0 is 2 here. So this means you have alpha squared minus 7 alpha minus 6 equals 0. We can simplify by eliminating alpha to the power n from this equation. And therefore, after eliminated alpha to the power n, you get this. Okay, this one is clearly a quadratic equation. So you have alpha, alpha. Okay, this one is pretty easy because you have the homogeneous in the non-homogeneous. Or okay, let's just finish this one. Let me see what you're getting here. Okay, what are the factors of these? So you have minus 6 minus 1. Alpha 6 or alpha 1. Okay. Let me just try to do it here. I can do it on the next slide. But there's an advantage of doing it on the same slide because we can see everything here. Okay, let's solve this together. So this thing here can be solved. There's something called the general solution of this. Then the general solution. The general solution is just put the roots. So it's going to be an is equal to. So you take an arbitrary letter A. You take 6, you raise to the power n. B is the next one. Alpha to the n. A is 2, A is that. Okay. What is A0? It's 2. The initial conditions, they will help us to find the A and the B. Okay, let's find A0. What is A0 if you make n 0 into this? So it's going to be exactly A plus B. Okay, you replace n, so 6 to the power 0 is going to be 1. And then this is 2. It gives us an equation. Call it equation 1. And then now the other initial condition is that A1 is 7. Right, so if n is 1 here, it's going to be 6 to the power 1, which is 6a. B is 7. Right, you subtract these two things. 2 minus.
Hello?
Yes, please.
I'm not sure if this part is right.
Which part? Oh, that part. Okay, let's check that part, please. Let's check it together. Okay, because we got this one and we're just eliminating the negative, the minus 2. So I just took a decision to multiply by alpha squared.
Here, here specifically,
Okay, there's a plus.
this
There's a
part.
plus. There's a plus, maybe. Okay, there's a sign issue. Um, okay. Okay, let's look at that part. Because there's a plus 6 here. That's all. Because the 6 was transposed and became, it was negative, it became positive. The 7 became, it was positive, it became negative, right? Is that all? I agree with you. So the 6 was negative and then
Yes,
became
that
positive.
that was the problem.
Please come again.
It was supposed to be plus.
Yes. Yeah, the 6 was supposed to be plus because it moved, it crossed the equal sign, right? Okay, let me analyze that with you. Let me analyze that with you. Just one sec. Right, so the 6 was negative and became plus. Good. But obviously when you're here, you'd have alpha to the power n, alpha to the power 2 minus 7, alpha to the power n, alpha to the power 1 minus 6, alpha to the power n equals 0. Okay, we've just separated these things. We transpose the 7, and okay, this one became plus. Okay, because it was negative, it became plus. And then we factor out alpha to the power n. Okay, this one is squared. So alpha squared, 7 alpha plus 6. Okay, so this can be factorized like that. So you can factor out the alpha to the power n. Basically, this would mean that alpha squared minus 7 alpha plus 6 equals 0. If that sort of resolves why we have this quadratic, and then the factors are indeed that, and we have that. Okay, let me know if there's anything of interest there. All right. Right. So from this, now we have the following. We have the 2 minus equation 1. Can deal with them by elimination. 6a minus a is 5a. 7 minus 2 is 5. Divide through by 5, we get that a, this is capital A. Okay, dividing through by 5, we get that a is exactly 1. So, okay, just made this one. Just made this one small, but it must be capital. Okay, now the capital, this one, 6a. Okay, subtract these ones, you get 5a. And it becomes that. Divide through by 5, you get that a is 1. Okay, if a is 1, then you can use any of the equations to get b. Okay, like, let's use this one. If a is 1 here, which means b is 1. Okay, so if this is true, then it means you can just plug in the a and the b into the general solution. This one, where that is a, that 6 to the power n, b 1 to the power n. So a and b are both 1. Okay, so the general solution would be an equals 6 to the power n plus 1. So this is the solution. Because we have to solve this recurrence relation, we solved it, and this becomes the solution. How do we know if this solution is correct? We can check by getting a0, the initial conditions. So if n is 0, then 6 to the power 0 is 1. So a0 is 6 to the power 0, 1. 1 plus 1 is 2. All right, and if we get this one when an, when n is 1. 6 plus 1, 7. So a1 is 7. So this is correct. Right, we continue. Next question.
I have a few questions.
Yes, please. Okay.
For this type of question, do you always do this?
Yes, always. Always, we always let an be alpha to the power n. Always. Okay, but obviously this one is the homogeneous. This is the homogeneous recurrence relation. I'm going to look at another example that involves non-homogeneous. Right, so the non-homogeneous recurrence relation is a little bit different. And we shall look at an example that involves that one. Okay, and so there's a small difference in the way the non-homogeneous. What would the non-homogeneous mean? Okay, we call it an inhomogeneous. Right, so this one is homogeneous. So I'm going to look at this and say, so there are two types. Okay, let me write in red. So you can just write two, homogeneous and inhomogeneous. Okay, so normally the homogeneous is the easier one. Because the inhomogeneous has numbers that do not have n. Like if I can subtract 3 over 2. Right, so let's look at homogeneous. What does homogeneous mean? Right, so the homogeneous recurrence relation. So the recurrence relations is either homogeneous or it is what you call inhomogeneous. Okay, sorry. But this one is pretty generally easy. It's easy to correct marks. There's just no confusion. Right. Right. So the homogeneous case would be of the form this one here. Right. The homogeneous will be of the form an equals c1 an minus 1 plus c2 an minus 2 plus br an minus r. So this is called homogeneous. So it has a's up to the end. Like there's n minus 1, then there's n minus 2. The others are just not there. You could have an minus 3. Okay, but it starts like that. Right. Now, what about the inhomogeneous? And now the inhomogeneous has its own slightly different method that we use. Right, so the inhomogeneous would be of the form an is equal to an minus 1. But now it's not only an's, there can be something else, some function of n. And now, obviously, we shall spend time on that on those because the inhomogeneous can be a little bit tricky. And now the homogeneous ones are easy to solve. But now to solve the inhomogeneous, you must make this one 0 and first deal with the homogeneous case using the substitution alpha n, and then you include this. So we're going to look at cases like those. Cases like those. Right. So the inhomogeneous case, if you're given an example like this one, right. So you can have this one, an. Need to solve this. I can always, if time is going to allow, I'm going to do an example. This example exactly. Okay, it can be minus 4n, then, okay, 3 plus by 2 to the power n. So you see at this point now, it's not only that you have the a sub uh, n minus something. Now this one is minus 4n plus 3 times 2 to the power n. So it is called inhomogeneous. Because of that, then we'd have to first deal with the homogeneous case. So what do? We first make this 0, use our usual a sub n equals alpha to the power n, and then get the general solution like we have done. And after that, we get something called the particular solution for this extra term that makes it inhomogeneous. Okay, so we're going to look at examples like that. But yeah, let's look at the next problem. Right, a very important concept is called the inclusion-exclusion principle. So the principle of use the principle of inclusion-exclusion to determine the number of arrangements of length n. Right, so n is at least three or more of the letters A, B, C, repetitions allowed, in which each letter occurs at least once. Right, so we are looking at the number of arrangements of the letters in which each letter occurs at least once. 8 marks. Right, you get this one, you already passed the exam. Okay, it's a lot of marks, but there's a bit more work there. So this one here uses a wide range of methods, but we start as follows. Using the inclusion-exclusion principle, you let A. be the set of arrangements um, of arrangements of length n. Of length n, arrangements of length n, call those A, with no small a. Let A be the set of arrangements of length n with no A. So, because now we are saying of the letters in which each letter occurs at least once. At least once. So you let B be the set of arrangements of length n with no B. Let C be the set of arrangements of n with no C. Okay, we understand why we are removing we're saying no A, no B, no C in each of those arrangements. So in principle, we want to determine the number of the arrangements. So the number of the arrangements, no A, no C. A, B, C. Like that. So we want to determine those where in which each letter occurs at least once. Okay. So if one determine the number of the arrangements in which you have the complement of A, the complement of B, the complement of C, which means it's a union complement. A union B union C complement. Okay, we can analyze what this means. But what is the total number of the arrangements? Total number of arrangements. Right, there are 3 letters here. So it's 3 to the power n. 3 by 3 by 3 by 3 by 3. Because the first, if you have these 3 letters, the first letter can be chosen in 3 ways. If you're looking at an arrangement of length n. The second one, you can choose, we have 3 choices, you have 3 choices. But now we need to do this until n. So we have 3 to the power n ways of this. Okay, next. Now, the number of the arrangements of the strings in A will surely be the number of the arrangements in B, because we're just saying no A, no B, no C. And it's also going to be the number of those, because in C we said the set of the arrangements of length n with no C, no B. So we're just removing A, B, C. So it's just the same number. So n number of the strings in A is the same as the number in B, the number in C, and we analyze what the numbers are. Right. So if we say there's no A, so if we say there's no A, then we're dealing with B and C. And the B and C can be organized in 2 to the power n ways. Okay, if there's no B2, you are dealing with no B, then you're dealing with A and C. Right. In C, I said let C be the number, be the set here of arrangements of length n with no C. No C means we're dealing with A and B. There are 2 of them. Okay. Continue. What about if we are to look at the number A and B, set A intersection B? How many combinations are these? Okay, so there are 3 sets A and B. So you can look at A intersection B, or you can look at A intersection C, the number of strings in A intersection C, or you can look at the strings in B intersection C. But there's no other, all the sets are taken care of here, but we'll look at all possible intersections of the 3 sets. So A means there's no A. In B, there is no B. Then I left with C. In A and C, in A, there's no A. In C, there's no C. You're left with B. So it's 1 to the power n, just 1. By 1, by 1, by 1, by etc. So it's 1 to the power n of those intersections of those sets. Goodness me. We continue. And if you have now the number of the, now if you intersect all of them, no A, no B, no C, you intersect all of them. What are you going to get? Are you going to get an empty set or what? Yes, because this one says no A, no B, no C. So it means they don't intersect these. The number of the elements in the intersection is going to be 0. Okay, good news. We'll continue. By the inclusion by the inclusion, exclusion, principle, okay, so you have A intersection B intersection C. Okay, good, good, good. We continue. So this one, complement of A, complement of B, complement of C. Okay, now this one has three sets. It has three, isn't three inclusion exclusion, it involves three sets. Inclusion exclusion, a principle that involves three sets. So the formula is that it is n for everything minus na minus nb minus nc plus na plus a b plus n bc. Okay, so we have these n and a and b and c and a. Okay. Okay, so you have this one in A, B, C. All right, so what is this? So you have complement of A, complement of B, the complement of the set C. Hey, goodness me. 3 to the power n is this one. Number of the arrangements, total number of the arrangements is 3 to the power n. And then now we have done the A, N, N, B, and C. A, N, A, N, B, and C is 2 to the power n, but there are three of them, so you can look at 3 times 2 to the power n. N, A intersection B, intersection C, B intersection C. Okay, it's 1 to the power n. You can view that as just 1. So if you add all of them, it's going to be 3. And then this guy here is 0. So you have this. So this is the result. But now let's analyze this together. Because the point of this discussion is to familiarize ourselves with the concepts and how these principles are used. We take questions that are common in the assessments and discuss them to make sure that we just understand what's happening. That's what this is about. And familiarize ourselves with the approaches that are standard. The aim is not just maybe to solve 1 million questions that do not even appear in the exam, but is to make sure that you understand the things that appear in the exam. Okay, if you use the principle of inclusion and exclusion, just passing through this once more, to determine the number of the arrangements of length n greater or equal to 3. Okay, obviously n greater or equal to 3 because now we're dealing with 3 symbols and repetitions are allowed, in which each letter occurs at least once. Okay, so if each letter occurs at least once, the easiest way is, for example, if you look at the set A and we say let A be the set of arrangements of length n with no A, what will the complement of A be? The complement of A, because A has no A. Set A has no small a. So which means that the complement of A is going to have what? It's going to have A. So because now then the complement of A is going to have A, because we're looking at the number of arrangements of length that in which each letter occurs at least once. So we decided to say, okay, let the A, B, and C be with no A, no B, no C. So that now if we deal with the, so we want to determine the complement of A intersection, complement of B intersection, complement of C. Why these complements here? Because now we are saying at least once. So the complement, if A has no A, then the complement of A is going to have A. So this one is A, and this one is B, and this one is C. But most importantly, it has at least one A, at least a B, at least one C. Okay. But now, if you look at the set theory according to De Morgan's law, the intersection here of A complement intersection B complement intersection that, we can take the union of these and take a common complement. Right, so this is in view of De Morgan. Right, is in view of what you call De Morgan's law. Right, I'm just going to comment on De Morgan, and then we're done. Right, so in view of De Morgan, what does De Morgan say? Well, De Morgan says that if you take the complement of this, if you have A union B, you have this. And then if you have this one, which is this. So, okay, I'm doing it for 2 sets here, but yeah, even 3 sets. So now we have A intersection, then it's the same as this, but now the intersections become the union when you take a common complement. The total number of the arrangements for all these, in how many ways can you arrange the letters A, B, and C? The first letter, because now you are arrangements of length n. Right, so where n is greater or equal to 3. So now the number of arrangements is going to be, how many letters are there? There are 3. So the first letter is going to be chosen in 3 ways. The second letter is going to be chosen in 3 ways, because how is this possible? I need to make this as practical as possible. So you can have a letter of length n, a number of an arrangement of length n. So that's going to be A, B, C, D. A, C, C, B. A, whatever. But now it's of length n. But in the end, now the first letter must be chosen amongst these. So you can choose it in 3 ways. After that, the second letter can be chosen in 3 ways. The third letter can be chosen in 3 ways. Okay, did I put a D? I meant this is an A. Okay, so you can have something like that. So yeah, it's ABC like that. So you have this. So now 3 times 3 times 3 times 3 times 3 times 3 times 3. So it's 3 to the power n. The length is n. Okay. I was then saying total number of the arrangements will be 3 to the power n. Now, n a, n b, n c equals what? Um, um, okay. So the number of the elements in A intersection B, A intersection C, B intersection C is 1 to the power n. Okay. And n A intersection B intersection C equals this. Okay, by the inclusion-exclusion principle, um, the number of the elements in A intersection B intersection C is, this is the formula for the 3 sets. Normally, we deal with the 3 sets, but yeah, we can also deal with um, 2 sets. 2 sets are easier. Okay, you've seen 2 sets even in school, but these are the 3 sets. Okay, let's deal with the 3 sets. Right, now the number of the arrangements, so all of them is 3 to the power n. The n, a, n, b, and c is 2 to the power n, but there are 3 of them. This one is 1, 3. And this one is only 3. Okay, so this is the answer. Okay, we are done with this question. And that is the answer. Okay, I believe it's clear. We move to the next one. Okay, there are things we call generating functions. Okay, here's the question 11 on generating functions. 15 marks, total marks. Right. So obviously we're dealing with the distributions and we mentioned the idea of distributions in one question. We're dealing with the world fulfilled, something like that. Yeah. Okay. Right. So generating functions to answer the following. Determine the number of the 10-digit 10 array sequences in which the digit 2 occurs at least once and the digit 0 occurs an even number of times. And the next question B. So yeah, I must have made a provision for space there. Okay. Um, the generative functions, the formulas are there at the back of the exam. So always they give you the formula for the generating functions. The power series are there at the back of the exam. Okay. Obviously, the power series are determined in other modules of mathematics, like your analysis, your real analysis module and your numerical analysis. That is where we develop a lot of the power series. But obviously, we use them here. We apply them to real life problems to determine the number of the 10-digit ternary sequences in which the digit 2 occurs at least once, but it's a 10-digit ternary, these are 10-digit ternary sequences, but in which the digit 2 occurs at least once, and the digit 0 occurs an even number of times. Okay, let's look at this. So, what is the answer to this? The digits. Right, because we're dealing with the ternary sequences 0, 1. It's not like binary 0 and 1, ternary. So 0, 1, 2. The digits 0, 1, 2 are distinct. So we require an exponential generating function. Right. Okay, there are more exercises we're still supposed to do on Hamilton paths, and because there are tricky questions that really can come from that area. Um, the chromatic numbers, we need to play around with more questions in isomorphic graphs and non-isomorphic graphs. And obviously, yeah, we had to delve into a bit more in-depth questions on those particular areas, right? But these digits are distinct and you require an exponential generating function. Right. Determine the number of the 10-digit ternary sequences in which digit 2 occurs at least once, and digit 0 occurs an even number of times. Okay, this is easier with the generating functions, but it can also be done using the methods we used. We can use, like, what method did we use earlier? Um, we had a similar question, very interesting. Okay, number of arrangements of those are, okay, we can use the inclusion exclusion, right? So is this one? Is the one before? Is this one here? Find the recurrence relation for the number of these. So you can determine the recurrence relation for the number of these. Okay, so it's one of those. Because this recurrence relation, you can solve it. So the kind of the question we're looking at now can be done using recurrence relations. But now we're going to use the generating functions to do it. But you can use recurrence relations, and now at this point you can solve, because this one is homogeneous. So you can just say an is alpha to the power n, and then you can solve this, and you can get the, using the initial conditions, you can solve this. Okay. It's okay. But now we're going to use generating functions just for us to use something different and learn something different. So the digits, these are distinct. So we require an exponential generating function. In this case, the generating function, the generating function is, okay, what is the generating function? Okay, so the generating function now is what? Okay, because you need to determine the number of the 10-digit ternary sequences in which the digit 2 occurs at least once and the digit 0 occurs an even number of times. Okay. Okay. I want us to analyze this together. Right, if the digit 2 occurs at least once and the digit 0 an even number of times. Okay. So you have x, one of the generating functions. I'm going to discuss this. We have x squared over 2 factorial, x cubed over 3 factorial, plus dot, dot, dot. Okay, this is one of the generating functions because the digit 2 occurs at least once. Okay, I'm going to discuss this in detail. I'm going to elaborate on this. All right, and the digit 0 occurs an even number of times. So if the digit 0 occurs an even number of times, it means that for the digit 0, you're going to have 1, and then it can, okay, it can be x squared, 2 factorial. You can have x to the 4th power, 4 factorial. Okay. Okay. You also have another generating function, x squared over 2 factorial. We shall discuss this. I'm going to elaborate on these generating functions and their significance in this kind of a problem. We have 3 factorial plus dot, dot, dot. Okay, let's pause to discuss a little bit briefly about the generating functions here and their significance in this case. Right, so what is the significance of the generating functions? Right, we discuss that one. Right, so the couple of things obviously that we need to learn here. If we say, for example, if we say you need to determine the number of the 10-digit ternary sequences, we are dealing with 10-digit ternary sequences, and that is gonna the 10 is gonna appear in the you will see the significance of the 10. But I want us to discuss the fact that the digit 2 occurs at least once. Right, so if the digit 2 occurs at least once, right, so at least once, so it means that you start from 1. The power of the generating function, the power of the x. So now the power of the x is going to, because it's at least once, it's going to be 1, 2, 3, 4, 5, 6, 7, 8, etc. So it can be those particular cases. It can be those particular cases. Right, so you note that. Right, so, but also now end means you multiply now, because you said that digit 2 occurs at least once. So 1, 2, 3, that. So you put times because there's and here. Right, so you continue and say the digit 0 occurs an even number of times. The digit 0 occurs an even number of times. So if the digit 0 occurs an even number of times, it means that you have even numbers. What are the even numbers? They are 0, 2, 4, 6, 8, 10, and so on. Those are the even numbers. So that is why here you're going to have, so this one is like x to the power 0. So you have x to the power 0, x to the power 2, x to the power 4, x to the power 6, and so on and so forth. Right. When the digit 0 occurs an even number, that's why you have those. And now you have also another generating function that is obtainable at the back of the paper. So at this point, what is evident is that you need to include the generating function at the back. Okay, I'm gonna just give a comment about that one there. Right. Right. So remember that we're dealing with the number of ternary sequences. What are the ternary sequences? For the ternary sequences contain, because we're dealing with 10-digit ternary sequences in which we have that. Okay, this is a very interesting problem. Uh-huh. Uh-huh. Okay. Right. Okay. Okay, I'll read you now. There's something I want to mention. Right. Okay, there's certain things we call types. There's certain things we call types when we're dealing with the generating functions, and I want to mention that. The types of things. Um, okay, the types of things. Okay, so this one takes care of what? This one takes care of 2. Of the digit 2. It was mentioned first. This one takes care of the digit 0. So this one takes care of the digit 1. Because we're dealing with the ternary sequences, and the ternary sequences would have zeros, ones, and twos. Right. All right. Okay, continue. So what does it mean? It means that the 1, there are no restrictions on the 1. So you take a general exponential generating function. This is an exponential generating function. Okay, let's multiply these things. So what is this thing here? Okay, this exponential is always e to the power x is 1 plus, this is the general one. So you have x squared over 2 factorial, then you have x cubed over 3 factorial. Okay, so, but now if you have just the x, and that, 1 plus x squared, etc. So now, this one now, because it's for the digit 2, it starts from x. So you must move the 1 to the other side. So it becomes exponential x minus 1. Okay, let's look at this one now. It's x squared over 2x. Okay, this one is having even things. He's dealing with the even things. What does dealing with the even things mean? Right, dealing with the even things, if you look at the back, this one is e to the x plus e to the minus x over 2. That is what is at the back of the paper. Then this one of 1 plus x squared, and that is the general e to the power x is always like this. Okay, so we have this now. We can just multiply everything. My goodness me. E to the power 3x minus e to the power 2x plus e to the x minus 1. So what is this? Okay, so this is actually 1/2. Okay. Okay, what is e to the power 3x? E to the power 3x is 3 to the power r. E to the power 2x is 2 to the power r plus 1 because of the e to the power x. Okay, why is it like this? It is like this because you have x to the power r. Like in real analysis, you can just make this r, but now you need to understand what that means, and you have r factorial. So, which means that if it's e to the power 3x, it means here, wherever there is x, if it's 3x here, you put 3, 3, 3. And then now these 3x is going to become like that. 3 to the power r. Then you have 2 to the power r plus that. So this is minus 1/2. We want the coefficient. Oops. Right, want the coefficient? What? Okay. Okay. I'm glad I did not get this deleted when I was pressing one button accidentally. Right, we want the coefficient of x to the power 10 over 10 factorial, which is, hey, can use the recurrence relations we saw before, and just to test the understanding of the method. But yeah, we had to need a bit more drilling on these questions because they can emerge a bit tricky sometimes. So it's 3 to the power 10 minus 2 to the 10 plus 1, you divide by 2. Oops. Like that. Okay. Okay, so this is the answer. We want the coefficient of x to the power 10 over 10 factorial. So the coefficient of x to the power 10 over 10 factorial. So it's going to be when r is 10 here. R is 10. When r is 10, it's going to be 3 to the power 10, 2 to the power 10 plus 1. Okay, over. Now you have the coefficient. Okay, sorry. It's going to be x to the power 10 and then 10 factorial, but it's going to be 3 to the 10, 2 to the 10, 1 over 2. That is the coefficient. It's the coefficient. And so that is the answer. So we have got the answer like that. Right, so I think that we've discussed these generating functions. All right, it is my plan that we have more practice questions, so I'm always thinking about what to do. So I'm thinking about tomorrow's plan of crafting a plan that is going to deepen our understanding about solving a wide range of questions on the things we discussed. Because this one was basically, question 11 was the last question. So tomorrow we're going to start by doing part B, because part B is also a little bit long, but we're using generating functions. Most of these questions that can be done using generating functions can be done using recurrence relations, the an equals an minus 1 and so on. Right, so how do you learn this and how do you practice this? First things first, these are like examples. So we did these as examples. So examples, how are examples studied? Examples are practiced and are practiced repetitively. So one repeats and make sure you understand these examples. You can sort of make sense of these examples, because I'm planning to bring more questions tomorrow. Right, I'll give you more information about the sources of these questions and where actually these questions come from. Okay, because there is a question bank I'm gonna mention where these questions come from. And I'm gonna bring more questions. It's my plan to bring more questions from the actual bank of the questions so that you can practice like the kind of the question we saw, the question about fulfilled, and so on. Okay, but I must thank you for joining us today. I think that the time is about. We can take it. We can take a break. It's about 16 hours, and I think we started about 1 p.m. 13 hours studies approximately. Because a few minutes after. Okay, thanks so much. Goodbye. Load shedding now.